What's up? I don't know why, but my timer paused there. So we had the wrong countdown for a bit. Alright, let's do this. Okay, so today we want to talk about trees, and we're setting you up to get programming task 5. So this is what we want to do. Program task 5. For this, you're going to use a binary tree. As a binary tree node, you're going to use it as a binary search tree, which we're going to talk about what both of these things are in today's lecture, of course. So you want to use it as a binary search tree. And we are going to cover the binary search tree class today. So you're able to just use that code from the examples repo to set this up. And our goal here is to create a playlist class that's going to take a comparator of songs in its constructor, which this is our payoff for setting up those comparators in task 4. We have the song title comparator and the song Bayesian average rating comparator. Both of those comparators can be used in the playlist class. So when you're testing, you create a playlist, give it one of those two comparators, or if you want, you can create a third comparator, whatever you want, but give it a song comparator. Add songs to that playlist, and these songs, when you call get song list, these songs should be sorted in order according to your comparator. So for example, the easiest one to use is the title comparator. Give it a bunch of songs using add song, give it the title, song title comparator in the constructor, and then call get song list and check if that linked list contains all of the songs in the right order that you expect according to that comparator, which would be alphabetical order by title. So that's what we want to build. That's what we want to build in this this homework. For the testing, I want to talk about testing first. I'll circle back to the testing utility method. For the testing, we want to test the playlist class, but not everything. Well, actually, it is everything. There's just not much there. The playlist class, we're going to call the constructor with a specific comparator, call add song a whole bunch of times, and then call get song list. As long as get song list, the one that takes no parameters, there will be two get song list methods. You only have to test one of them. I'm going to test the other one, but you only have to write tests for the one that takes no parameters. Call this one that takes no parameters and assert that it gives you the right song list, the right songs in the right order for this method. This method returns a linked list of songs, and what I really want to point out right now is the importance of using your utility methods. I'm starting to see way too much of this. I won't have time to do a lecture example about it, but I'll give at least an explanation of what I'm talking about here. Is every assignment sets up, aside from task 1 and task 8, has a testing utility method, and that testing utility method is intended to be used in your testing. Like, your testing should be easier because you have the testing utility method. And and I'm seeing a lot of issues. The reason I'm bringing this up is I see a lot of issues, a lot of Piazza questions, a lot of office hour questions that with issues that would never exist if the students were just using, if those specific students were using their testing utility method. And I kind of suspect that anybody who's hearing my voice probably doesn't need to hear this, so I don't want to harp on it too long. I'll try to keep this brief. But even if you get this point, it's helpful to have a reminder, I think, of why we're doing things the way we're doing. Is you write the testing utility method to help you whenever you have to compare two values in your testing. In this case, it's going to be get song tree. You have a compare song trees method. The idea is that for get song tree, you're going to call the get song tree method. That's going to return a tree. Then you're going to manually create your expected tree. What do you expect that tree to look like? What do you expect the structure to be exactly? What do you expect it to look like? Create that tree, and then call compare song trees with those two trees. Then compare song trees does all the work. And then make sure that you're asserting what this returns if you don't have asserts. If you ever have return false in this method, make sure you're asserting what it returns. But use your utility method to do your comparisons for you. There's a reason that we built all these utility methods. It's to make your testing a lot easier, so you don't have those the issues that come up. It's usually students who want to shortcut the testing. They want to save time, and of course, they, as always is the case, end up wasting more time doing the homework the lazy way instead of just setting up your tree, because it can be kind of a pain setting up your tree in this one. It was a pain in test 3 setting up your linked lists. I assume that's why a lot of students didn't do it, because they don't want to do extra work, but then they got to post on Piazza and come to office hours and wait for answers and wait in the queue. It's so much more of your time. Just do it the way I'm showing you, please. I'm pleading with you. Use your utility methods. Compare song trees will already handle all the edge cases and everything. Because you already wrote that code and this was already tested by Autolab, confirmed to be correct. So use that when you're doing your get song tree method. That's the intent of all of these utility methods, is you're going to have a chance to use them in your testing requirements. You're going to have a chance to make these tests easier to write by using your testing utility method. And then there's get song list. This will return a linked list of songs. And I want to point out that we have other utility methods here, which I think I say this up. I guess I say it right here, because these will be binary tree nodes of songs, but you'll also have to test a linked list of songs. So when you're testing the linked list of songs, you can still set up your helper methods. For one, we already set up a method that will test linked list of ratings. So each song now has a linked list of ratings in it. And we also set up a utility method that will compare to songs. We have compare songs, but when we wrote compare songs, the songs didn't have ratings associated with them yet. So you have a few choices. You can either add to this compare songs method a call to the ratings, compare linked list of ratings, compare list of ratings, whatever I called it, method, or just make 2 calls. In your testing for task 5, when you get the song list, for each node in the linked list, call compare songs and call compare lists of ratings on those songs .get ratings, whatever the getters return. And then you won't have any issues related to that anyway. You might have other stuff, but you won't have any issues that might be caused by that. I see too much of, I have a specific example in test 2. I know it's an old example, everybody's passed this one, is compare ratings. Specifically when students, I've seen this from a lot of students, like every semester, a lot of students do this exact thing, is when they're testing the reviewer.rateSong method, they'll neglect to call these helper methods, the utility methods. Of course, that's why I'm talking about it right now. They'll neglect to call them, and they'll recreate all the work that they did in those methods, and they'll check the reviewers to make sure the reviewer.getReviewerID returns the right thing. They'll call rateSong, and they'll check the rating that's returned and make sure it has the right rating by calling getRating, but they'll never check the ratings reviewer ID to make sure it got the right reviewer ID based on the reviewer that created that rating. And I don't know why, but that's just one that students always forget. But if you're calling compare ratings, you cannot forget that, because it's already done. You already did it, and you already had it checked off by Autolab. Autolab already said, oh, your compare ratings is fine. Create your expected ratings and your expected reviewers, your expected songs, your expected linked list of ratings, which is the first one that gets a little tricky because you have to create a whole linked list. It's not that bad. We've done it multiple times in lecture. Create your linked list of ratings that you expect. Create your tree that you expect. Create your linked list of songs that you expect. Create those expected values and then call your utility methods. And you might want to add one for linked list of songs that calls all your song utility methods. So one part that's not explicitly required of you to do for get song list, but I strongly recommend doing it. Most of the null pointer exceptions in task 3 would be avoided if students would always call their utility methods. And the same thing is going to happen here. This is these binary tree nodes. They do use null in the same way that the linked list did. And also you have an explicit linked list when you're getting the song list. That's a linked list also. And each song has a linked list of ratings. So we're using these node-based data structures that use null as part of their structure. We're using them all over the place here. So null pointer exceptions can, if you're not careful, come back in a major way in task 5 if you're still not fully grasping that concept of checking for null. You always have to assert if something's null. Never assume that it's not null. Assert that it's not null, which you can't make that mistake if you use your utility methods. Depending on how you check the linked list of songs, how you create that utility method, because that one's not checked off by Autolab. So those are all the warnings I want to give. Like if you follow the structure, do your testing utilities, use your testing utilities when you write your tests, and then use your tests when you're writing your code. If you follow that structure that's laid out, a lot of the Piazza and office hour questions wouldn't exist. You just wouldn't have those questions. So again, that's where I want to cap that, because again, anyone who's listening to me isn't going to have those problems. Like maybe you just forget when you do it. Maybe you don't fully understand exactly what I mean, and you don't think of it when you're coding. Maybe. Skipping the intro, not watching lectures live, skipping the intro, going right to when I start covering content, new content, and then watching it 3 times speed. Like that's what I assume a lot of students are doing. Like we have 12 live right now. Like there's a lot of bad habits out there. When you say assert not null, you mean do null checks in the utility method, right? Yes. Yeah, if you're doing your null checks in the utility method, then you don't have to think about your null checks again. But you're just calling your utility method, which already does all the assert not nulls. And the utility method's already checked in Autolab. So Autolab's already making sure you have your null checks, which most of you in your utility methods, the first thing you do will be your null checks. Most students will. But if you don't call your utility method in your tests and you're recreating all that work that you've already done, I see a lot of students do sloppy things with that. And by asserting not null, really what you're doing is assuming the size of the list that's returned. Yeah, assert that is what I mean is assert, like assert true, assert equals, and there's explicitly assert null and assert not null are 2 different asserts that you can use as well. So when I say assert, I do mean like in JUnit calling one of those assert methods. That's what I mean by assert. So assert not null, you could do assert true node not equal to null, or you can use assert not null of node to assert that it actually is not null. Because if you don't assert that it's null, if you just assume that it's null and you start using the dot operator on it, and it was indeed null, that's your null pointer exception. So you have to assert, is this thing not null? If it's not null, then let's go on to the next test case, the next assert. Doing the test during lecture, I mean, that can work. Is if you're watching lecture, like if you're doing task 5 during this lecture, if that's what you mean, then yeah. But some students skip lecture to do like task 4 to catch up on tasks. Like that's a bad habit. So it depends exactly what you mean by that. But I personally like doing that as a student. Like I'll work on the homework that the professor is currently teaching me how to do. Like that's how I can stay exactly right on top of the material with that habit. Paying attention, of course, and then, if I understand what's being said, then I'm going to apply it directly to the homework. If I don't understand what's being said, well, I better believe I'm going to start paying attention and set the homework aside. Yeah, but if you call your utility methods, you don't really have to distinguish between asserting not null, assuming not, like, you don't even have to think about any of that, except when you're writing your utility method itself. But from what I see, like, you're all pretty good at understanding that when you're writing the utility method, it's when you skip calling the utility method, and then you do something. A lot of students will do something like call the method that you're testing and store that in a variable called node, and then say assert equals node dot get next dot get next dot get value dot get rating equals 5. Like, you'll do something like that right away. But now you have a lot of dot operators on those get next and node itself, all of which might be null, without ever asserting that they're not null. So you get a null pointer exception somewhere in there, because what you're doing in that specific example is assuming that the size of the returned linked list is at least 3. So if what's returned isn't a linked list with 3 nodes, one of those get next or the node itself is going to be null. So if it returns a linked list with 2 nodes in it, and you say node, which is the head, dot get next, which is the second value, which is also the last value, dot get next, that's going to return null because now you're past the last value, dot null pointer exception. You can't do dot get value on that because it's null. So you have to assert, make sure that it's not null. But your utility method, compare lists of ratings from task 3, already did that check. If Autolab checked you off on the utility method, that means you've already handled that case. Create your expected linked list of size 3 in that instance, or more, and then call your utility method. You won't even have to think about it. So we do code. Oh, I forgot about that example. We do code, and it always feels so long going from Thursday to Tuesday. I feel like I gotta remember everything. We're good though. We got this. Oops. Okay. And I don't have to go to the slides at all today. This is going to be purely... Actually, I take that back. I do want to go to the slides for the last bit after I cover BSTs, the last bit of what would be Wednesday's lecture. So let's create a binary tree node class. So I want to create a binary tree node class. I want to create binary trees. And binary trees, we're going to see, are very similar to linked lists. They're a node-based data structure. So we have a node class, and a reference to a node is going to be how we represent, how we store our binary trees. And the big difference is that instead of a reference to, actually let me just code up, get a little code before I make this point. We're going to have a type parameter. I used A in the slide, so I'll use A here. And we have some private A value, just like we did with the linked list. Except now, instead of having one reference to another binary tree node, we're going to have 2. So instead of just one reference to one next node in the linked list, now we're going to have 2 references to 2 different nodes, and we're going to call those left and right nodes. And we're actually going to call those child nodes. There's a whole family tree analogy that spreads throughout binary trees, where we have the left child, the right child. This node is the parent node of its left and right children. And it does extend. We won't. I'll use child node. That's the only one I'm going to use in 116 outside of this little blurb right now. But when you do study trees further, like in 250 and 331, and if you ever study them beyond that, the analogy does stretch further. Grandchild, grandparent, descendant, ancestor, cousin, aunt, uncle, niece, nephew. Although the whole analogy can just keep expanding the way you want to explain it. However you want to refer to 2 separate nodes as relationship to each other. There's also a nature analogy that spreads through all this. So there's two separate analogies we have for all this: the actual physical trees in nature. So in linked list, we had a reference to the head node, and that was the first node in the linked list. In trees, we're going to have a reference to the root node, and that's going to be the first node of the tree, is the root node. And then there's branches and leaves and forest, a bunch of ones that we're not going to really talk about in 116. Okay, and I'm going to start using some shortcuts here. I hesitate to ever use this in lecture, but it is so useful that I don't want to have to do all this. I'm going to tell IntelliJ to create my constructor for me. I think I already used the getters and setters in lecture before, but generate getters and setters. I'll say this with a warning. IDEs are very powerful, useful tools. They can write a lot of code for you very quickly, especially when it's boilerplate code like that. But you have to understand what the IDE is doing for you. It's of course academic integrity to use the AI, the autocomplete stuff, which very unfortunately is by default on in IntelliJ. I really wish it wasn't. So if it's writing full lines of code for you, or full methods even, you're at risk of an academic integrity violation. Just warning with that. That is not allowed. But when it's boilerplate, creating like getters and setters like this, use at your own risk, but it is allowed. But use at your own risk. If you don't know exactly what it's giving you, because once you use something like that and it doesn't give you the right thing, and you don't understand what it did for you, oh boy. There are a lot of developers out there right now who are very dependent on AI to write code for them, and I really fear for them. They're going to have that day where the AI just doesn't do it for them, and they have no clue what to do because they're missing they have huge gaps in their understanding. And I honestly I worry about students who do use that and don't get caught. Ideally, they just get caught, and then we say try again. But if they don't get caught, they're not hireable. And the whole point, my whole job is to help you get a job. And I don't know, it's hard for me to watch that when some students do end up getting away with it. When I get them in my upper level classes, and I get students who can barely write a line of code, and they're in my office hours and can't even write a loop in a 300 level CSE class, and I'm like, you used AI through every single course, didn't you? Holy shit, you don't know a damn thing. Why are you here? I don't want to go any further on that. I could rant about that all day. I got to stop, because you're not the audience that's doing that. Anyone hearing my voice, actually watching lecture, that doesn't describe you. So here's my binary tree node class, and this is it. If you look at the example repo, what was here, what I deleted, it does have more methods in here. It has the traversal methods inside this class itself. I'm not going to do that when I'm writing the code live. I don't like that those are in the class, the binary tree node class. So I'm not going to do that for my example here. I'm going to do that differently. And I decide exactly how I want to do that. And I have to think ahead to the memory diagram, because I don't want to set this up in a way that's going to be extremely tedious. But I might just end up doing that anyway, because I might not plan ahead good enough here. Well enough. So I have my binary tree node, and let's see how to use this class. Let's create a binary tree. And in the examples repo, I do create this a different way. I've done it a few different ways. In the live, there was a little bit of live coding at the end of the 8 a.m. lecture, and I did it another different way. Actually, I probably will still do that when I get to that part of this lecture. So there's a lot of different ways to do this that achieve the same goal. But let's set this up in a way. I'm just going to do integers because it's easier. Set this up in a way that's going to make the memory diagram not too bad, which is the same way that I set up these sample. Oh, I forgot to mention. On Piazza, I posted sample quizzes, a sample OOP quiz and a sample data structures quiz. Those quizzes are going to look eerily similar to what you'll see on both the midterm and final exam on all of the quizzes. So study those, make sure you understand how those work. Both of those samples cover every concept, every learning objective that I need you to know. Do y'all stop? Send me notifications. Everything that you're going to need to know from 116. So when I come up with the quizzes for the midterm and the final exam, they're going to look the same because I'm assessing the same thing. And it's kind of boiled down to the bare minimum. Like there's no extraneous stuff there. I'm not just adding stuff to add tedium to the quizzes. So they're going to look eerily similar. You're going to pull up the midterm and say, boy, this looks very, very close to the sample, because they're going to assess the same things. And that's what I want. I want you to understand the concepts, how everything works in the samples, and then show me on the midterm, and hopefully not the final, but on the final if you need it, show me that you understand how that works. You're going to get similar code. It's going to be different enough that you can't just memorize the solution to the samples, but not so different that it's going to look like a completely different thing. All right, so we call the reference that we have the root. Is going to be a new binary tree node, and let's just give it some value here. I'm not going to remember all the values that I gave in the slides, but we'll do our best here. And you know what? I lied. I'm not gonna do this the same way as the. How do I want to do this? Oh, the memory diagram is going to be such a pain. I think I'm going to waste more time trying to figure out how to make the memory diagram easier. I'm just going to make a memory diagram that's a bit painful. Actually, I'll create a second tree that's a little smaller for the memory diagram. So to indicate that there is no left or right child, we're going to use null. So this isn't like a linked list where once we get to null, we're at the end of the linked list. Once we get to null here in a tree, that means we've reached the end of that branch. And that's going to indicate that there's nothing more at that location. So this would be a tree with one node with the value 5 and no left or right child. And then we can say root dot set left to new binary tree node with the value 3, or just whatever value, I'm just making them up, null and null. Root dot is these setters that are going to be a pain on the memory diagram. New binary tree node 8 null null. Maybe I will trace this one. So let me just do 4 nodes here. Root dot get left dot set right. New binary tree node. So we went left to 3. So let's add 4 right here. 4 null null. This should suffice. That should be plenty fine. I'm gonna print line nothing, just so I have a spot for a breakpoint. I want to show you how this looks in memory. So I'm creating a new binary tree node with the value 5 and no left or right child. And then I'm going to set its left child. So I'm going to replace this null with a new node with the value 3 and no child nodes. Set its right to a new node with the value 8 and no child nodes. And then root.getLeft.setRight. So in these 2 lines, I've replaced these 2 nulls, but all these 4 nulls are still there. Now it's root.getLeft, root.getLeft, which is going to get this node here, a reference to this node, dot set right, so set this node's right child to a new node with the value 4. So when I look at this in the debugger, oops, that was the wrong thing. Yes, I know that. No test found. So when I look at this in the debugger, I'm going to get the variable root, which is a reference to a binary tree node. I got 528 here. And when I take a look at its instance variables, I have value, which is 5, left, which is a binary tree node for 532, which should have the value 3. A right child, which is a binary tree node 533 with the value 8. That's the one we created right here, which is the one we set right for. And then the left child also has a right child, so it's getLeft.setRight. GetLeft was a reference resolved to this reference 532, and we said setRight called from this node here. It's right. We set it to a new node with the value 4 and a left-right of null. So this is our binary tree. This is the structure of a binary tree. And that's all I have to say about the structure of a binary tree. That's it. This is how we use it. And we're going to create our binary trees manually like this. We're not going to have an insert or add or prepend, append. We're not going to have those methods in the binary tree node class itself like we did with the linked list class. But we will when we create the binary search tree class, the BST class. That's when we will write an insert method which will use a binary tree node as an instance variable. But this is it. It's like a linked list, but there's 2 references. So this is a different way to set up the tree. In the quiz, on the sample quiz, I set each binary tree node equal to variables, and then instead of setting all of my constructor values to null and then replacing them, instead I would have like node 3 inside the constructor call. Makes things a little more clean for the quiz. I probably will do the same thing on the midterm, just because I think it makes a cleaner memory diagram. But I'll show a different way here. I'll use the getters and setters and just have a whole bunch of getters and setter calls. It's going to be a pain. Let me get rid of this print line. I only had that so I had a spot to put the breakpoint. Okay, so that's a binary tree. That's it. We got that. Now, my code is giving error that it can't be applied to int null null. You don't have int here, do you? This would, I don't think it'd give you that error though. Do you have your type parameter? Maybe you're missing this entirely. If you're missing this, then you'll get... Oh, actually it didn't give issues. What could you be missing that would cause that error? All your type parameters are set up the right way. And you have integer here. You have your type, your angle brackets here. Oh, looks like that wouldn't cause the error either. Without seeing it, it's going to be hard to debug. Something's missing. If you're using the binary tree node class that was already in the repo, this code should work just fine. I don't know. I'm trying to think of what other typo would make that cause that specific error. I'm probably not going to be able to debug it in chat. I gotta keep moving. But if you have more hints for me, let me know. If you see anything strange. Or if you see anything, if you catch anything. Alright, so our question, because that's the structure of a binary tree node. Can come to office hours. Yeah, cool. I'll see you there. It's going to be bugging me now, though. What would cause that? Can't apply to... I'm assuming you're using the class from the repo, so this would have to be right. And then some int value null in the constructor of the binary tree node. And you have new, right? Would missing new cause that issue, that specific issue? Can't find local variable node when. Yeah, I don't know. I'm blanking on what would even cause that. Okay, so the question is, so this is our structure. The question is, how do we work with this structure? Like how do we do anything with this? And the big, easiest question I want to ask is, how do we just visit every node in this tree? All I want to do is visit every single node and print out all of the values of this tree. Just print everything to the screen. That's all I want to do. That's all I want to do right now. For the homework, you'll want to traverse an entire tree and create a linked list of songs based on a tree of songs. So we got quite a bit to get to before we can do that. Let's just visit all the nodes and print everything to the screen for now. And we're going to see 3 different ways to do this. I'm actually going to create static methods here because we don't really have any instance variables that we're worried with, so we don't need to reference this, a reference to the calling object, excuse me. And we're going to see 3 different traversals. I'm going to start with in order traversal. I guess I didn't have to call it traversal. I could just say in order. It's going to return void. We're just going to print things to the screen. If you look at the lecture slides, we actually return a string and then print the whole string all in one go. I'm not going to do that here. So we're going to take a binary tree node of integers. And that's the node that I'm currently visiting. I'm trying to think of how I want to do this. I'm going to do it the other way. Screw it. If you're confused by this, just ignore what I'm doing. But I'm going to use a type parameter here. I forget exactly where it goes. Not there. Right there. So methods can actually take type parameters. So now this can work with binary tree nodes of any type instead of hard coding it to integer. But so far, type parameters, we always saw them applied to the class themselves, which applied to the objects when we called the constructor. But methods can take type parameters as well. So I'm going to do that. If this confuses you, forget about it. It's not something I'll... oh my god, I just ranted about that. Do not use AI. Like, that's an academic integrity violation that you're admitting to in chat during lecture. Turn off your AI. I can't even... I can't even. Like, especially when it causes... I just ranted about that. If you're going to use a tool like that and then not even understand parameter orders, stop using the tool. Stop. And then expecting me to fix it. You didn't even write the code. You want me to debug code that an AI wrote. Where are you in this equation? What are you doing? What are you learning? Oh, that's frustrating. So what we want to do is traverse this tree. So I'm given a node. At first, this is going to be the root node. So in my main method, let me split this. Let me split this like this. So in my main method, I'm going to call my traversals dot in order traversal. And I'm going to call this on the root node. Like, that's going to be the use case here. Oh, I can't even type it. I'm going to call this on the root node of my tree. So initially, node is going to be the root node, but then I want to use this traversal to go through all of the nodes of my tree. So it's initially the root node, but I'm also going to use this as a recursive method. Yes, recursion is coming back in a major way. and and yeah, but by default, and I really hate that IntelliJ does this. By default, the autocomplete is AI assisted, which I think moving forward with this course, we have to not use IntelliJ anymore, just because it basically tells you to cheat. It's ridiculous. That's just a default feature these days. Autocomplete's fine. You see me use autocomplete constantly during lecture, but you've never seen my autocomplete fill in arguments for me. When I do new binary tree node, it autocompletes the rest of the word that I'm writing. So it finishes binary tree node. It will not fill in my arguments for me because I'm using autocomplete, which just completes the word that I'm writing. You're using AI assistance, which is not allowed. It is cheating because you're not learning. You're not even learning parameter order. That's a 115 topic that you have issues with. If that did make it to office hours and you're like, I got my arguments in the wrong order, which makes sense why students get the song arguments in the wrong order all the time, which is why I have the song class take 3 strings. So you have to pay attention to the order, and the AI will get them wrong all the time. Humans won't. If you're actually writing your code, you don't make that mistake. Well, sometimes. I shouldn't say it that strong. It's a mistake that could be made by humans. Okay, so for a traversal, we want to visit every single node. We're going to use recursion for this. And this is where it's going to come up kind of related to what I was just ranting about. In test 3, I say it's recommended that you use recursion, but you can use loops. But I strongly recommend you get practice with recursion during linked lists, whether recursion's easy, because it's going to get more difficult. And this is where it gets more difficult. This is the trickier recursion, but this is where recursion is really going to be helpful and powerful. Like, I'm going to write some code here. It's going to look like the code does nothing, but it actually does everything. So what I want to do is make recursive calls to in-order traversal on node.getLeft. I'm going to make an in-order traversal recursive call to node.getRight. And in between here, I'm going to print out this node's value. And if I run this code, here, I'll run it, I'll show you. When I run this code, I'm going to get null pointer exceptions. Null pointer exceptions are going to be a big deal whenever you're working with linked lists, trees like this. You're going to get null pointer exceptions if you're not careful. So this comes back in a major way. We always want to make sure we have our null checks. So I want to check for null here, and there's 2 different ways I could do this. The way I'm going to do it right now is if node is null. Actually, let me do it backwards. If this node is not null, then I want to do all this code. And if it is null, I just don't want anything to happen. So my base case of my recursion is when the node is null, nothing happens, and I just return without making another recursive call. If the node is not null, then I can safely use the dot operator on node. So before I use the dot operator, I have to make sure what I'm using the dot operator on is not a null node. Because a null node means there's no child, there's no node there, there's no reference there. So now that I know node is not null, I can use the dot operator. Now get left and get right might return null, and I might make recursive calls with null as the value, but then that recursive call is going to check for null before using the dot operator. I'm not doing dot get left dot, because right there I'm going to get a null pointer exception. I'm going to send it to the next stack frame. It's going to check for null, and then if it's null, just don't do anything. And if I run this code, what I should get is going to the root node when I have this called with the root node, I'm going to make the left recursive call, which is this node here, which is going to make a left recursive call, which is a call to null, which is going to do nothing. It's going to return back to the stack frame with this node, print the value 3 to the screen, then make its right recursive call, which is this node here. It's going to make its left recursive call to null, which does nothing. Print 4, make its right recursive call to null, which does nothing. Then return back to the stack frame with this node, which will return back to the root node, which will make its right recursive call to this node, which makes its left recursive call, which is null, it does nothing. Then print 8, then make its right recursive call, it does nothing. Then return and return. So we got 3, 4, 5, 8 is the order that we're going to make these calls in, that we're going to visit the nodes in. Now there's 3 different traversals that we can use, that we can write. There's in order, pre-order, and post order. Let's get rid of this. And the difference in these 3 traversals is, of course, the order in which we're visiting the nodes. So there's not in this case. So can we do assert not null here? We can't because we're not in a JUnit test. So there are times where we have to do not equal null or equal null. But if you're in your test, if you're writing a test case with JUnit, that's when you can bust out the assert not null. So IntelliJ forced you to do? IntelliJ never forces you to do anything. IntelliJ is a tool that you're using. That's like saying my hammer told me to smash my thumb. My hammer forced me to do it. This is a tool. You tell it what to do. So the difference between these three traversals is when you visit the node. So we have 2 recursive calls. That means we have 3 choices of when we visit the node, either before both recursive calls, after both recursive calls. That's our pre-order for before, post-order for after, and in order, meaning we visit the node right in the middle, right in between the 2 recursive calls. And that's how we visit every node in a tree. In order, pre-order, post-order, traversals. 3 different methods, but they're basically the same. The order is going to be different. So if I do pre-order, I'm going to visit the node's value before making recursive calls. So we always expect the root to be first, then the left 3 is going to be next, and so on. I'm not going to go through the whole thing. I did it in the other lecture in the slides, and I don't know. I think y'all get the point long before then, long before I go through everything. And then post order, we're going to make both recursive calls, and only after both recursive calls are done do we visit the node. So if we think about just the root node, we're going to go to the left, which is going to visit the entire left subtree. So the left child and all of its descendants, we're going to check all those. Then the right child and all of its descendants, and then the node's value. So we would always expect the root node's value to be last in a post-order traversal. So that's kind of our sanity check to make sure we got the order right here. And these 3, like I said, they're very similar, but you do have to pay attention to which one you're working with. This is one warning that I have to give. I don't have to, but one warning I like to give to students, because I see this a lot, is for this quiz, any quiz that contains trees, I see a lot of students over-studying for it. And what I mean by that is they'll memorize whatever memory diagram I did in lecture and try to just regurgitate that on the quiz, on the midterm in 2 days. By the way, the midterm's in 2 days. Isn't that crazy? And just regurgitate it. So whatever I do in lecture, which is going to be a post-order traversal when we do the memory diagram, I'm going to leave this as post-order. If I'll see students just barfing up post order in lecture. I'm also going to do a style of traversal where I am making the recursive calls on null, like I explained. I don't like doing that on the memory diagrams just because it's very tedious. You'll see when we go through this one, I have a lot of stack frames that just have node is null and doesn't do anything. A lot of node null. So on the sample quiz, I check before I make the recursive call, I check for null. I check if the node's left is null. Don't make the recursive call at all. So it really trims down the stack frames that I get. So I'll see whatever I do in lecture, like that's what I'll see a lot of the students who are failing the quiz. I'll just see basically my lecture example, but with the tree that I gave on the quiz. And that's not what I'm asking you to do. That's never what I'm asking you to do in all of computer science. None of your instructors are going to ask you to just regurgitate what you've seen in lecture. The whole point that I feel like I just made this point in this lecture. The two lectures blend together though, so forgive me if I repeat something there. But I think I did, so I'll keep it brief. But I'm arming you with tools, and you have to take all the tools that you're given and then use those tools to solve new problems that you've never seen before. That's the whole purpose of what we're doing here, because that's what you'll have to do on the job. Nobody, I think it was actually in the other lecture when I said this. I don't think I said this in this lecture yet. It's nobody's going to hire you, much less pay you a six-figure salary, to regurgitate my lecture examples. No one cares. Nobody gives a shit about what I covered in lecture when you're out there on the job. Nobody cares. That's not what you're asked to do. That's not what you're being assessed on at all. What they want you to do is solve their problems. Now, I can't prepare you for every single problem that every single employer is ever going to give you for your entire career, for all of your careers. I just can't do that. It'd be a miracle if I could, but I just can't do that. So what I have to do is show you the concepts and then assess if you are able to apply those concepts to new problems that you've never seen before. Now, they're going to look similar to the lecture examples. They'll be similar to the practice quizzes, but they're going to be different enough that you actually have to understand the concepts that we were showing in lecture, because that's what you have to do. Like you got to get there. You got to be at that level to be able to get a job. Or else you'll never get past the interview stage. When they interview you for tech positions, they can smell bullshit from a mile away. They'll know if you used AI on every single assignment and don't understand anything. It's easy to tell. Within seconds, by the way. Just to clarify, trees will not be in the actual quiz. Trees will be on the quiz, yeah. That's why trees are on the sample quiz, because they're on the real ones. All of them, all four of them. Both midterms, both final. The DS, the data structures quizzes will all have trees. For traces, you said you need to trace out getters and setters, but when you have a conditional statement, if you're discussing, like for the, wait, what? For traces, you said we need to trace out getters and setters. Yes, you should. Again, that's something I would never fail you for if you forgot your getters and setters, but they should be there, and they'll be there when I trace through this code. If node not equal null, wait, but when you have a conditional statement like you're discussing now, like if node equal, it's a twofer. If node not equal null, since there's no method call, you don't have to trace that, right? Correct. Yes. Yeah, so there's nothing to trace here because there's no getter or setter. And if this is true, if this is false, nothing even happens. There's nothing to trace. So when I do get to the trace, I'll have a bunch of stack frames where I'm putting the post-order traversal call on the stack, putting node null, and then just crossing out the stack frame right away. All of DS 1 through 3 and all of classes 1 through 3. No. If you're referring to like the old numbering of the quizzes, it would be DS 1 through 2 in classes 1 and 2. So DS3 and classes 3 from previous semesters, those don't exist in this summer semester. So DS3 would have been graphs, and classes 3 would have been polymorphism. Neither of those topics are going to show up on any quizzes this summer. It's linked lists and trees, and classes and inheritance for data structures and classes, respectively. Okay. Oh, and I gotta throw down the gauntlet too. I gotta challenge you. Those of you who are naysayers about recursion, do me a favor and try to write any one of these traversals. These traversals are as simple as they can be. They just print every value to the screen. Try to write any of these without recursion. With linked lists, that was easy. You could set up your loops. It wasn't that bad. For trees, just try. Just try. You'll see very quickly that it's very difficult. Try to set that up in a way that's going to visit every node exactly once. It's a lot more work. Like, I did this in 5 lines. I can guarantee that. Like, that's what these methods do, is they visit every node exactly once. Doing the same thing without recursion is a pain. It is very painful. Like line 13, you don't have a note. You don't have to note that anywhere. Sorry, I got confused sometimes. No. Like, the stack frame would go on the stack, and you'd say node is equal to null. But then for any of the code, there's nothing of relevance in memory. Nothing changes in memory. So you wouldn't trace anything for the actual execution of that method. You would just put the stack frame on the stack and then cross it out right away. And we're about to go to the memory diagram, so let's do that now. Let's compact this a little bit. I'm gonna delete my getters and setters, if I can be so bold. Just in hopes that I can fit all of this without having to scroll a bunch of times. And I don't want this to be called post-order traversal, just because that's extra typing. This should be fine. Why? Why is it asking me every single lecture to log in? My laptop doesn't do this. It keeps me logged in. There we go. Oh yeah, I got plenty of space. Move this over. All right, let's try this. This memory diagram is going to take a while, so I'm going to keep an eye on the time a little bit, but the timing will be a little different than the 8 a.m. lecture. But I got to at least do one trace with a binary tree. We got to see a binary tree. Okay, so we're going to start with the main method. I didn't even... Let's fix that. We can fix that. We don't have to live with this. I missed my start of my main method. My main method header. Format it. Refresh. I'm going to be staring at this memory diagram for quite a while. I don't want to... live with a main method header missing. We will need a few IO lines. I gotta watch my face because I'm gonna be covering this up. Okay. That should be good. We might not have room for all 4 lines here. Maybe I'll adjust later. But we'll worry about that when we get to it. Okay, so we start with the main stack frame. Let's try to get through this. There's gonna be a lot of minutia here. Root is going to be a new binary tree node, so stack frame binary tree node, which that one's going on my clipboard. This new heap object binary tree node, this is the parent. It's going to have value, left, right, our instance variables, this we got OX02 is going to return to root, and our parameters value left right happen to match exactly our instance variable name, so that won't always be the case in name or number. And this is 5 null null. Those all get assigned, the instance variables all get assigned the values of the parameters, and this returns OX02. I assume I can blow through the constructors pretty quick here. Here we have a new constructor call, and I want to delete that. I'm going to clone the stack frame, create a new, which I think I tried this earlier. I can't clone a heap object. Value left, right, uncross, move return arrow. This got OX03. The value was 3. 3 null null, 3 null null. This is where memory diagrams really get bogged down. This returns, and when that returns, I can finally put set left on the stack. So root.setLeft, create stack frame set left. This is the root, OX02. And this constructor returned into the argument, which is set to the set left parameter, which I removed my setters, but this should be left, is what it should have been called, OX03. The auto generation for that code, it was not AI generated. It's consistent. It follows a certain formula where it's getters and setters with naming that makes sense, at least makes sense to me. Set left. So then set left is going to say this dot left equals left. So this gets crossed out and OX03'd. This returns void, so there's no return arrow. Then we do the same thing a few more times. I'm going to try to just rip through this, but clone stack frame, value left, right, 4, 8, clone set right, OX04 right, OX04, create a new node, clone a new binary tree node. This is where I missed the slides, where I can just click once and say, there's all our constructors and getters and setters and all that. OX05, 4 null null, 4 null null. Returns doesn't return to a variable, so we don't have a return arrow. It returns to the set right method. We can't resolve the set right method until we resolve get left. So create stack frame get left on root. Get left. This is OX02. Get left is going to resolve. It's going to return this dot left, which is OX03. So this resolves to OX003. Then we're going to create a stack frame set right, where this this is OXO3 because that's what get left resolved to. So OXO3 and right is going to be that new node that we just created, OXO5. That's what the constructor resolved to. Set right this dot right equals, oops, cross out OXO5. This resolves, and we can finally get to the traversal. Look at all the space that takes up too. Okay, now we can get to the traversal. This is a static method, so we don't have to worry about this. We're going to create a stack frame for traversal, and I'm going to put traversal in my clipboard. Actually, I'm probably going to copy this stack frame a whole bunch. Traversal, there's no this because it's static, but we do have node, which is root, which is OXO2. So we go through traversal. It's not null, so we do traversal of get left, and this gets tedious. Should I even finish this one? I might bail on this. Get left, this OXO2. As soon as y'all get the pattern, we might bail. I don't know. We'll see. So get left, this dot get left is OXO3. So we're making the recursive call on OXO3. Or maybe I should have just went to the slides for this one. This one's tedious. So now we have a recursive call on OXO3. It's not null, so it's going to get its left. O3 get left is null. So we're going to create a stack frame traversal where node, this was supposed to be node, where node is null. And this is what I was talking about before. Node is null. So we put the stack frame on the stack, but since node is null, nothing actually happens. Nothing happens in memory. We look at the value of node, check if it's null. It is, so this resolves to false. And nothing happens, so we just cross it out. We're required to trace getters and setters. Though if they're on a quiz, they will be explicitly written out. I'll have the getters and setters in the code. I just, for the lecture example, I removed them. So we'll have to pretend they're there. For a quiz, any code that I expect you to trace, I will give you the code for that. So we're back in this call. Oops, sorry, get left. These resolved. So now traversal resolves, and now we go back to this frame. Finally, after all that, I get to make my first point. When we get back to this frame, this stack frame has to remember where it was in its execution when it made this traversal call. It has to remember that it was making its left recursive call. So when we get back to this method, this stack frame, it knows that it was waiting for this call, which just resolved. So now it can move on to this call, the right recursive call. So now this stack frame is making its right recursive call, get right, where this is OXO3, and get right, this dot get right is OXO5. So this resolves, and it resolves to OXO5, and now we're creating a traversal stack frame where node is OXO5, and this is the right recursive call from this stack frame. So this stack frame, when it gets control again, it's going to remember that it was calling this right recursive call. So when it gets control for the third time, it needs to move on to printing out that node's value. So this traversal of OXO5, OXO5, left and right are both null. So hopefully we can shortcut this one a little bit. Create stack frame, get left, this OX05, which returns create stack frame traversal node null, which does nothing. Now we're back in this stack frame. It just made its left recursive call, so now it's about to make its right recursive call. This OX05 that resolves to null. We create a traversal stack frame where node is null. That does nothing. Now we're back at this stack frame for the third time. The first time we visit a node, it makes its left recursive call. Once that resolves, the second time we make the right recursive call. The third time we get back to this node, we're actually doing something. We're calling get value, where this is OX05 in this case, which resolves to 4. So this stack frame can print 4 to the screen. We finally get our first thing that does something. Print 4 to the screen. And then this traversal is done. We're done with OX005, and we go back up to the next stack frame on the stack that's not crossed out. This is the top of the stack again. It gets control, and this OX003 node made its left recursive call and made its right recursive call, and now it's ready to print out its value. So now we get value, where this is OX03, which returns 3, which gets printed to the screen. So we get our second piece of action here. Now this traversal is done. Stream is frozen. Oh, this is my camera again, isn't it? No, it seems to be fine. Okay. Yeah, that might just be you. So this traversal is done. Cross it out. Go to the previous one, OX02. This was the root node, and it just made its left recursive call. Now it's got to make its right recursive call on OX004. Let's get a whole bunch of more stack frames on here. Sorry, get right. This OX02 resolves to OX004, and we're going to make the recursive call on OX004. And this is the first time we're on this stack frame, so it's going to make its left recursive call. And OX004 is, I never filled out the values. This is going to be 8, null, null. So we should be able to rip through this one pretty quick. Get left, this OX004 returns null. That's traversal, where node is null, which does nothing. Get right, this is OX004, which returns null, which is used to call traversal, where node is null, which does nothing. Brings us back to traversal. We can get this node's value. Which returns 8. And we can print 8 to the screen. This method call gets to the end of the method, traversal cross out, go back to the last uncrossed out stack frame. It's back to the root, which just made its right recursive call. So we're finally ready to print out the root. Now post-order traversal, that's what we expect to be the very last thing that's printed out. So get value where this is OXO2. That resolves to 3. Oh, sorry, 5. I panicked for a second when I saw 3. 5 is our root. I was looking at the highest number and didn't shift my eyes over a little bit. Print 5 to the screen. Then that original traversal call is done. We get back to the main stack frame, which doesn't do anything else, and it just returns. Holy crap, we made it through that one. Yeah, no problem. I do, when there are stream issues, yeah, please still always say something. When there are stream issues, I want to know about them. Because there's few things that are worse than going through a whole stream and realizing like an hour of it's garbage and nobody could hear me and I was just talking to myself in my office. Like, that's annoying. So I do want to know if there's any possibility that there's a stream issue. Please always let me know. Even if it might just be a local issue. I want to know. So that's that memory diagram. So I do like to set up quizzes a little bit different so we don't have all of these calls where you're just clicking through and not really thinking. You're not really being assessed on any learning objectives. You're just remembering to put all of your calls on the stack. I don't like that on a quiz because even I almost got lost in the details here and lost track of what I was even doing because I'm okay, get left, get right, get value, traversal of null. So I like to trim that down for quizzes, but it will be the same idea for the quiz. It'll look more in style of the sample quiz, though. That was more thoughtfully designed to cut down the number of calls. On the fly in a lecture, I just wasn't able to think it through well enough while I was writing the code to get rid of all the extra minutia of this. Okay. We can move on. We're done with that memory diagram. And I'm not doing another memory diagram today. That's it. I don't have to do another one. Let's get this code back in working order. Binary tree node needs its getters and setters back. And that should do it. Okay. So now we're moving into the Wednesday lecture. That one went a little over, but that's actually expected. The Monday and Wednesday both usually go over by quite a bit in the regular semesters, and then the Friday's more lax. It's more examples. But there's 2 topics I got to cover. Trees, and then BSTs. So let's do BSTs. BST. Okay, so BST, binary search tree. A binary search tree is just like a binary tree. It's built on a binary tree, and by that I mean there's going to be a binary tree node, which is the root of the tree, and it's going to take a type parameter. So it's going to have a binary tree node as an instance variable. So this is using a binary tree, or is a binary tree, depending on how you want to look at it. It's composed of a binary tree, to say the proper OOP term. And this binary tree is going to have 2 special properties to it. We're going to first have let's set a little bit more up here. We're going to have a comparator. And we're going to have a constructor that's going to take a comparator. Public BST comparator of A, comparator this dot comparator equals comparator. This is an example, by the way, of a constructor that doesn't take all of the parameters matching all of the instance variables. In this case, what I see a lot of times is in memory diagrams for the constructor, students will put root in the stack frame for the constructor, but it's not there. It's not a parameter. It's not declared as a local variable. Root doesn't exist in the stack frame. It only exists in the object that's being created. So the parameters for the constructor do not always have to match one-to-one for all of the instance variables. Most of the time that'll be the case. We want to initialize all the things, but not always. And this is a case where root, we want it to be, let's be explicit about this. We want this to be initialized to null. That's how we're going to represent an empty tree is null. Just like we had an empty linked list, it was null. Okay, so now that we got the setup, the binary search tree, a BST, has two very important properties. For every single node in the BST, everything to the left of that node has to come before that node's value according to the comparator of that BST. For my examples, I'm going to use the less than comparator. So in this lecture example, I'm going to say less than and greater than. I'm going to assume that it's the less than operator for our comparator, for our comparator in the lecture example. But in general, it's going to be whatever the sorted order is according to that comparator. No, there won't be any feedback. So I wanted the submit button just so you get a full feel of how you're going to use the tracing tool, but we're not going to grade those on the quiz. I will release my solutions to those. I'll post them on Piazza later today. After I got this lecture, then office hours, and then I'm going to catch my breath for a minute, and then make the solutions to those and post them on Piazza. So you'll have the full solutions of them. So everything less than a node's value is going to go to the left, and everything greater than that node's value is going to go to the right. Actually, I do want to jump to the slides for a second just because it's a lot easier to show this one visually. So like this is a BST. This node, the node with the value 5, everything to the left, the entire left subtree is going to be values that's less than 5, assuming, again, our comparator is less than with ints. So less than 5 to the left, greater than 5 to the right. And that applies to everything, not just the immediate child, but all of that child's descendants as well. So 2, -3, 4, they're all less than 5, so we good. 8, 7, 14, all greater than 5, so we good. But the property has to apply to every single node. So when we go over to this node with 2, to the left, -3 less than 2, we good. To the right, 4 greater than 2, we're good. 8, 7's less than 8, 14's greater than 8, so we're good here. So all nodes comply to the standards, and all the rest of the nodes have no child nodes, so nothing to worry about. So this is a binary search tree because the property holds for every single node in the tree. It's going to be by generic comparator, but again, I'm going to say less than and greater than often. Now, we do have a decision to make whenever we use a BST in our code is how we're going to handle ties. So if two values are equal to each other according to the comparator, what do we do with them? The way I write the code today, I'm going to break ties arbitrarily to the right. I'm just going to say, if it's a tie, go to the right. You could also say if it's a tie, go to the left. As long as you're consistent, it's not going to break your algorithms. And sometimes it's the case where you don't want to allow ties at all. For example, if you have a BST that's representing a key value store where you can't have duplicate keys, you might just not want to allow duplicates at all. And that's a perfectly valid answer. But either way, whenever you use a BST, you have to make a decision of what to do. For your homework, our decision is, let's just not worry about it. Let's just not. So I don't have any test cases that test for duplicates, that test with duplicates. I don't expect you to have test cases that test for duplicates. If you write a test case that has duplicates, you're probably going to have issues in Autolab, because you have to make a decision of how to handle duplicates. And if your solution and my solution make two different choices, then you're going to get test failed a correct solution. Just don't write any test cases with duplicates. I didn't write any test cases with duplicates. We're just not going to test with duplicates. We're just not going to worry about it. So that's my solution in 116. Otherwise, I'd have to have an extra bullet point on the assignment, and then it'd be one more thing that you have to worry about that's not really related to the learning objective, so I don't really want to add that to the homework. It's just a nuanced case, and it gets really painful, especially if I force you to make test cases that are the same. Now you're creating two songs with the same Bayesian average rating, and I don't know, things just get messy real quick with that. And it detracts from what I want you to do. What I want you to do on task 5 is traverse a binary search tree specifically, and use recursion to create a linked list with all of the values in the BST with an in-order traversal. That's what I want you to do. That's what I want you to focus on for most of the time. And also the testing utility method. How do I get two trees and traverse both trees and see if they're the same, while doing all my null checks, making sure I don't get any null pointer exceptions. Those are all the things that I want you to focus on the homework. We can ignore the possibility of duplicates. That just detracts from what I want you to actually be getting out of the assignment. Okay, so with a BST, knowing the property of a BST and how we're setting it up in the code, there's two methods that I want to write. Public void insert and public boolean find a value. I want to write insert and find. These are the two methods that we want to write today. How are we going to add values to our BST, and how are we going to find values? Insert returns void, just inserts the value. When we're inserting, the big key part of inserting is going to be maintaining the property of a BST. Now this BST is initially empty, and insert is the only way we have to add values to the BST. So if insert maintains the property of a BST, then the property of the BST must always hold true, if this is the only way we can get values in. Now, that's not 100% true. We can never really guarantee something like that. Since value is a reference to an object, somebody can go to the heap and mess with that object after inserting it in our BST. So, if you're not careful, your BSTs can break because we're handling references. But as long as there's no funny business going on like that, and you're careful about how you code, insert maintains the property, which means the property will always hold. When we code find, we're going to be on the other side of that. We're going to assume that the property holds and take advantage of the property of a BST to be able to efficiently find our values. And efficiency is the key there. It was also the key to linked lists. I didn't emphasize it all that much with linked lists. I will emphasize it a bit more with binary trees, because you should be always asking the question, like, why are we learning this? Like, what's the point? And the point of learning all these data structures, because a good counterpoint to me showing you linked lists and BSTs and graphs is, well, I could do everything with an array list. Like, why would I bother with a linked list at all, of all things, much less a BST? And the answer is efficiency, which is like the core topic of CSE 250. You're going to see all these data structures and compare them to each other based on their efficiency, and learn how to choose the right data structure for the right application. So efficiency is the big answer, but we don't really care about efficiency in 116 necessarily. So I'll talk about it a little bit at the end of the BST coding, but it's really a 250 topic. So it'll be up to them to really show you why we learned all this stuff. With 116, I just wanted you to know what these data structures are, how they're constructed, and a couple of algorithms to work with both of them. Then they'll both come back in a big way, big ways, linked lists and trees and graphs and others, hash maps, a bunch of them in CSE250. So how do we efficiently do this stuff? Which we won't even get efficient, spoilers, but we won't even get efficient today. Actually, before that, let's do usage. BST of integer BST equals new BST new int increasing. I'm going to borrow that from week 7. So we have our comparator class, just a quick refresher. And then int increasing. We did int decreasing in lecture, but int increasing is your standard comparator, your standard less than, which will sort your ints in increasing order. So we're going to sort in increasing order for this example. BST dot insert 5 8 3 1 7. Sure. So BST dot find 1 6 5. Sure. Let's run this just to be funny. It's going to be false, false, false. Because of course the method just returns false and insert doesn't do anything. So let's implement these methods. Now that we have some sample code that we can run, we expect to see true, false, true to be our final output here, which is a horrible test case. Like you can get this by pure chance. There's only 8 possible combinations of outputs for these 3 calls. So yeah, even if you're just completely random, just flipping a coin here, you have a 1 in 8 chance of passing this if it were a test case, which is bad. Your test case shouldn't pass incorrect code 12.5% of the time. But just to give some sample usage of this. Okay, let's get on with it. Insert. So we need a null check. Right now, the root could be null. In fact, the first time insert's called, root will be null. So I can't do root dot anything in this method without checking for null first. So if this dot root equals null, if the tree is empty, or just isn't easy, this dot root equals new binary tree node. Create the thing, give it the value that we're adding. Null, null. It's the only node in the tree. It becomes the root. That case is easy. There's nothing there. Create the root. This is the first value that's ever been inserted in this BST. If not, we have an issue here. We would like to do recursion, right? We want to insert the value. But if we just do this dot insert value, we don't progress at all. The only way we progress through a recursive call is by changing the parameters, and the value that we're adding isn't ever going to change. So we want more information here. What I want is the node that I'm currently visiting, and I want that node to start at the root. This is what I would like, so that's what I'm going to get. I'm going to create a helper method. It can be private because nobody has to care about the details of how I write this method. I'm going to call it helper, insert helper, because that's how I like naming my helper methods, to make it very clear what they are. It's going to be a binary tree node of A, which I'm going to call node, and then a value. And now the way I'm going to write this, I'm never going to call this method, this is kind of the other way that I was saying of doing things. I'm never going to call this method with node. So I'm always going to do my null checks before making recursive calls, as opposed to doing my null checks at the beginning of the method. I'm going to do them before I call the method. So a little bit different, just to show you different flavors of how to do this, how to accomplish the same goal. So I'm going to assume node is not null. It's true already. If node is null, we're doing this. We're never making the recursive call. So node isn't null yet, and we're going to be careful when we make our recursive calls to make sure that node is not null. And this is where I'm going to use my comparator. If this dot comparator dot compare the value that I'm trying to add and this node's dot value. So if node could possibly be null, right here is where I would get my null pointer exception. I know it's not going to be null because I already checked for null. So I'm going to compare. Does the value I'm trying to add come before the value at this node? If it does, then according to the property of a BST that I'm in charge of maintaining, this value has to go to the left. I have to be thinking left. So I'm going to take a quick peek over to the left. I'm going to say, hey node, what's your left look like? More specifically, is it null? Do you have a left child? I always have to have my null checks. If I don't have my null checks, I'm going to get null pointer exceptions. So I'm going to peek left, and I'm going to say, is it null? Because, look, I got this value. It's got to go to your left. And if your left is null, I just found a home. I just found a home for this value. It's going to go to your left. It's going to go to your immediate left. If I peek left and it's not null, now recursion to the rescue. Insert helper. I'm going to restart this method. I'm going to go back to the top of this method with the left node, this node's left node as the parameter. And for the value that we're inserting. We're still inserting the same value. So the value, if we ask the comparator and it says, hey, the value comes before this node's value, we're going left. Otherwise, we're going right. We're going to do the same thing, and I'm even just going to do a sloppy old cut and paste. Get right. Get right. Set right. If this returns false, that means this value comes after this node's value in the fully sorted order, or they're tied. They might be tied, and this is where I'm going to break ties arbitrarily to the right. If I inserted the same value again, I'm just going to put it over to the right. And everything will end up working out with that, but again, we're not going to worry about that on the homework. We don't have interviews, so it can't come up as an interview question, and I'm not going to do that on a quiz. But that's just so the code has to be complete, and I'm going to break ties to the right. And that's our insertion. Can we add a helper method for task 5? Absolutely, yeah. That's why I show you helper methods so much in lecture, because it can help in your specifically for your get song list method. But at the same time, I kind of set up your helper method for you. You have to have a method that takes a tree node as well, in addition to your one that takes no parameters. So that second one kind of is your helper method. So I set it up a little for you. But if you want a third method, another helper method, because you want another parameter, go for it. If you want to take references to linked list nodes to keep track of the nodes that are being returned, that might be something you want to do. Maybe, maybe not. Just depends on how you want to set it up. A lot of different solutions to that problem. That you can do it that way. Okay, and this is insert. So let's run this in the debugger and take a look at how this rolls. So at first, BST's root is null, which I'm gonna squeeze in as much debugger as I can, which still isn't all that much. But the debugger, if I haven't given this speech in this lecture yet, oh my god, the debugger can save you so much time. If you have any bugs in your code, run the debugger. It'll show you exactly what's going on as your program executes. And it's just absolutely eye-opening, the amount of information it shows you. Get practice running this debugger. It'll save you tons and tons of time. So I call insert. I'm going to click the step into button, which is going to advance to the next line of code while going into any new stack frames that are created. So I call insert with 5. I get a new stack frame for insert, and the debugger will tell you which line we're on as well. So this is on line 18 right now. I advanced to line 19, and root was null. This dot root is null. So we go into this conditional, and we set the root equal to a new binary tree node. This is where I'm going to use step over. This is the second most useful button. Step over is going to advance one line of code, but it's going to skip any method calls that are made. So I don't want to go into the binary tree node constructor because that's boring. So I'm going to do step over and then make sure that this .root is now a reference to a binary tree node with the value that I inserted. It is. So now I have BST root has the value 5. Left and right are both null. That's what I expect after inserting the very first value. And comparator, for what it's worth, is hanging out there. Now we're going to insert 8. Root is not null, so we get into our helper method. The node we're currently considering is the node at 535, which is the only node, but it is the root node as well. And we're going to invoke our comparator and say, is the value that I'm adding, which is 8, does it come before this node's value, which is 5? And since it's the less than comparator, this is going to say false, so we're thinking right. And I'm going to skip over the calls. I don't want to go into the getter. I don't want to go into compare, which just does less than 2 ints. So I'm going to step over all that. We get to the right node. We're going to check if the right is null. It is. So we're going to create a new binary tree node, call the setter. I don't want to go to any of those method calls, so I'm going to do step over as well, here as well. So we just added 8. I'm going to skip over 3 as well. Let's skip over 1 as well, and then we'll go into 7. So after adding 3, what we expect is that's going to go to the root, which is 5. It's less than, so we're going to think left, and we found a home. Left was null. So we found a home for it right there. We added 1. We looked at the root, which was 3. We thought left. We found a node there, so we made a recursive call. Found 3. 1 is less than 3, so we thought left. We found null and inserted 1 to the left of 3. Now with 7, root is not null. Start our recursion. 7 less than 5 is false. So we're thinking right. Right is not null. This node's right is another node, this 537. So we're going to make a recursive call to insert helper. So we're putting another insert helper frame on the stack. And this time node is at 537 that we saw before, the root's right node. So now with this recursive call, we're acting as though this is the root node of the tree. We're acting as if no other nodes exist except this node and any of its descendants. And we're going to say, okay, I'm inserting 7. The value at this node is 8. 7 is less than 8, so I'm thinking left. Left is null, so that's where we're going to insert this value. So our final tree is the root of 5, left of 3, which has a left of 1. And the root's right is 8 with a left of 7. So we can look at the whole structure of the tree after inserting those values. And this is the exact structure that we would expect there after inserting. I got lost on timing, right? Till 1:30, 45 minutes. Okay, we got plenty of time. All right, so let's do find. So that's insert. We're maintaining the property. When we write find, now we get to take advantage that that property exists. And for this one, I'm going to return a Boolean. For linked list, our find method returned the node that contained, the first node that contained the value we were looking for. Just to show you that that is a common thing that we like to do in programming with these node-based data structures. I'm going to skip that with this one and just return a Boolean. whether we found the value or not. So we need our null check, very first thing. If this dot root equals null, there's nothing to do. If the tree's empty, I don't even care. I don't even have to look at the value we're looking for. The answer is no, it's not in there. Else, and we have the same situation here. We want a helper method. Actually, with this one, I'm just going to call it find. Since I do that on the homework, where you have to have two methods named getSongList, I'm going to name this find. It's going to return a Boolean. It's going to take a binary tree node of A, and call that node, and a value. And then call my helper method return find of this dot root. We're always going to start our search at the root, and then forward value, the value that we're looking for. Then we're never going to call this with null, so we want to say if this dot comparator dot compare of value, we're going to make the same comparison we did with insert. Value and node dot get value. We can assume that node is not null. We're not assuming, but we know node is not null because we checked for null here, and we're going to be careful in all of our recursive calls that we don't call it with null. Notice that our recursive calls in insert, it was always in the else of a null check. So if we got into this else block, we know get left isn't null. It can't be, or else this would have been true. Same with the right. If this is true, we go here. If it's not true, that means get right is not null. So we're going to pass it to the method, which is going to assume that its parameter is not null. So we always have our null checks. They always have to be there. One way or another, you got to get your null checks in there. So if the value comes before, remember this is less than, so if this value comes strictly before, compare is only going to return true if the first argument comes strictly before the second argument. If that's the case, we're looking left. This value can't be the value we're looking for because it's a strictly less than, it's strictly before comparison. So we're thinking left for sure. And what we've just done is eliminated the entire right subtree. Anything to the right can't possibly be the node we're looking for because it comes before this node's value, and by the property of a BST, everything to the right of this node's value, that entire subtree, has to have values that are greater than this node's value or equal to. That's the way we're breaking ties. Since this returned true, the whole right subtree is not a viable, not part of the search space. We eliminate that whole part of the search space. So we're thinking left. So let's check if left is null, because we don't want to make any recursive calls before doing our null check. If node.getLeft equal null, well, that means we can give up. We didn't find what we're looking for, just return false. Else, we want to make our recursive call. We want to move over to the left node. So we're going to make our recursive call on node.getLeft, and we're still looking for the same value. Now here's where things start getting a little bit different from insert. We actually want to do another check here. We want to do this dot comparator dot compare. This is where we're going to see the full power of our comparator. We're going to do node.getValue value. So we're going to ask our comparator another question. It's a very similar question, but a little bit different. We're going to say, hey comparator, does this node's value come strictly before the value we're trying to insert? If the answer is yes, then we know we have to look right. We can eliminate the entire left subtree, and we know we're looking right. So if node.getRight, if the value's in the tree at all, it has to be to the right of the node we're currently visiting in this recursive call. And if the right is null, that means we've run out of search space. There's no other possible place that this value can be. So we return false. Else, make our recursive call to the right. So we move over to the right. Find right, and we're still looking for the same value, just forward it to the next stack frame. Now here's the beauty of our comparator. If we said, does the value we're looking for come strictly before the value at this node? And it says no. This value does not come strictly before the value at this node. And we flip it around and say, does the value at this node come strictly before the value we're looking for? And it says no again? That can only mean one thing. This is the value we're looking for. So the comparator returns true if the first value comes strictly before the second value. If it returns false twice when we swap the parameter order or the argument order, these values must be equivalent according to the comparator. Now they might not be actually equivalent, but according to this comparator, their fully sorted order does not matter. If their order was switched in a fully sorted list, that list would still be sorted either way, no matter how we order these two values relative to each other. This doesn't always have to be, missed my returns here. That's the errors that I'm getting. Return whatever recursive call returns. If both of these are false, they have to be the same. Now they don't have to actually be equal. So we can't we don't get the same thing from dot equals, but according to this comparator, in one case that I've been kind of beating you over the head with on the homeworks, is that if our comparator compares two strings while ignoring case, like these two strings might be very similar strings, they might be the same characters but with different capitalization, the comparator that ignores case is still going to say that they're the same order according to the comparator. It's going to return false both times, but they're not identical strings. Like if you dot equals those strings, it's going to return false. So not necessarily equal, but equal according to the comparator. Their relative order is irrelevant according to the comparator. Okay, let's head back to the debugger and do some find. I gotta stop the debugger, set up a new breakpoint, run the debugger. We get the same tree that we had before. We're going to try to find 1 in this tree. In this tree where the root is 5, the left of the root is 3, left of 3 is 1, right of the root is 8, left of 8 is 7. So in this tree, we want to find the value 1. We're going to check the root. We're going to check the root. Root's not null. Get through that one first. We're going to check the root. We're going to say, does the value I'm looking for come before this node's value? That comparator is going to return true. So we're going to think left. We're going to look to the left of this node. We're going to check if it's null. It's not null. It's definitely a node and it has the value 3. So since it's not null, we're going to make the recursive call with node being that left child and start this method over again. So let's start the whole debugger over again because I clicked a little too greedily there. I don't want to go into get left, but I want to go into find. I want to go into the recursive call. So we put a new call to find on the stack. That call, the other call is waiting at line 54 for this recursive call to end. And now we have the value 1 that we're trying to find. And at this node, we have the value 3. We're going to ask the same thing. Does 1 come before 3? It sure does. So we're thinking left. Left is not null. It is a node that has the value 1, which happens to be the value we're looking for. Make a recursive call, add another recursive call to the stack, and start over again. Now the node is this node at 538. This is what node is. And we're going to check, hey comparator, does 1 come before 1? Does the value I'm looking for come before the value of this node? And it's going to say no. 1 is not less than 1. So it's going to make another check. It's going to invoke the comparator again and say, well, does this node's value come before the value that I'm looking for? Is 1 less than 1? It's going to say, no. You just asked me that. They're the same values. Like, what the hell? the only other option is these are the same value according to the comparator. In this case, they are actually equal, of course. I mean, they're both 1. So we're going to return true and say, yep, we found what we were looking for. Return that all the way up the recursion, and we can print true to the screen. With 6, I don't want to go through the entire thing. Oh, oops. Well, I didn't go through any of it. With 6, we're going to check the root node. Does 6 come before 5? No. So we do our other check. Does 5 come before 6? Yes. So we're going to get into the right subtree. So we're going to go into the right subtree, and now we're at the node with the value 8. We're looking for 6. Does 6 come before 8? Yes. So we're thinking left. We're going to make our recursive call. Since left is not null, we're going to make our recursive call and move over to the left to this node with the value 7. And we're going to check, does 6 come before 7? Yes. So we're thinking left again. This time left is null. So we found our answer. The value's not in the tree. Return all the way up the recursion that the answer was false and print false to the screen. We can do 5. I'll do 5 also. So 5, get into our recursion. Is 5 less than 5? No. Is 5 less than 5? No. Return true. We find the value right at the root. Nice case. Nice, very efficient. Nothing more to do. Okay, and here's the part where I do want to go to some slides. I like to limit my slides in the 11 lecture. For this one, I have no idea how to convey all this information accurately just by rambling. So I want to talk about balanced binary trees. By the way, this is the tree that I used in the slides, the lecture example. This tree was always balanced. The one I used in the code just now wasn't balanced, so this is referring to the one from the slides. But that example is a balanced tree. It's nice and symmetrical. Every subtree at each node has the same number of descendants in it. So it's a nice balanced tree. If a binary search tree is balanced, then the height of the tree is log of n, or O of log of n. It can be off by constants. Is O of log of n. And that's the height of a tree is the path, the length of the path from the root of the tree to any null. So the longest path specifically is going to be the height of the tree. So what's the longest you have to go to get from the root to the furthest null? How much harder would it be to return the location? Not at all. When I return true, it would be return node. That would be the only difference. I just felt like doing it some other way. I don't remember why. And then all the falses would be changed to return null. So it would be super easy if you wanted to do. I think I did that because it's less useful to have a reference to the node in a BST. The reason it's helpful to have a reference to the node in a linked list is because often you're finding a specific spot in the list because you want to manipulate some references. Like you want to add a value to the center of a linked list, or not necessarily center, but somewhere in the linked list that's close to a node with a specific property. So for example, if you're creating a linked list and you want to insert the values in sorted order, you would find where that location is for the new one you want to add and then add it. You don't want to do that same thing with a BST because you're risking destroying the properties of a BST. You always want to insert values using your insert method to make sure you preserve the BST property. So given just handing out references to nodes in the middle of your BST is just asking for trouble. I think that is a reason to do that. I think that's the reason I thought about when I wrote the code. If not, I'm going to stick with that one because it absolutely makes sense. So the height of the tree is log n, and insert and find, notice we did, and I'm going to use a bunch of efficiency talk here. I'm not going to assess you on big O notation and efficiency stuff in 116. This is all 250 stuff. This is like a foreshadow CSE 250. But I want to talk about some of it here because it is the motivation of why to use trees. Like we would just use array list for everything if it weren't for efficiency, like I said earlier. But I want to do some explanation of why that's the case. And it's because insert and find take log of n. Each recursive call takes constant time. It takes the same amount of time no matter how big the tree is. And we have to make log n recursive calls in the worst case because sometimes we have to go from the root down to the furthest null. So it's O of the height of the tree, which is log n for a balanced tree. And for what it's worth, we have another sorting algorithm that's O of n log n. We didn't talk about any in 116 this semester, but you saw merge sort very briefly in 115. We have another O log n, n log n sorting algorithm because if insert takes log n time and we insert n values into the tree, we have n unsorted values, we add them all into a BST, and then we do an in-order traversal, which will take n O of n time. Then we have an n log n sorting algorithm by just calling insert n times and in-order traversal. Oh, I forgot about that one. Ooh, it's a very important thing to say. I went on the slide too. In-order traversal of a BST is going to visit all the values in sorted order. So for your homework, you can use the BST class, by the way, that's in the examples repo, or the one that I just coded now. They're pretty much identical, if not actually identical. I used find instead of find helper would be the only difference that comes to mind. But you can use that BST class as an instance variable in your playlist class, insert into the BST, and if you do an in-order traversal over the BST's, that underlying tree in your BST, you will visit the songs in sorted order. So do an in-order traversal. This is the most useful traversal for our purposes in 116, is an in-order traversal. So in-order traversal will always visit all the values in sorted order. In-order traversal visits everything to the left, then the node, then everything to the right, which sounds exactly like our property of a BST. It'll visit everything less than, visit the node, and then everything that's greater than, according to the comparator. In-order traversal is your friend in task 5. And you can use the BST code. The homework isn't about recreating a BST or anything. I need to show you the code for a BST to talk about BSTs in lecture, and then it doesn't make sense to just have you like retype what I showed you already. So you can use the BST class, and then the homework is all about traversing trees. How do you traverse a tree and visit the nodes in order while creating a linked list with all the values, which is not trivial. It's not super easy. It's definitely the hardest thing that's shown up on a task so far, by kind of, I don't want to say a significant margin, but it's definitely the hardest thing that's shown up on a task so far. But that's what I want you focusing your energy on, not recreating a BST that I already showed you how it works. And the big advantage to a BST, getting back to runtime, biggest advantage of a BST is that it can maintain sorted order even with dynamic data. If your data is changing a bunch, I always think of a global leaderboard. You got millions of players of your game, and you want to maintain a leaderboard of all their scores. Their scores are constantly changing, and they're constantly moving positions. You can't maintain that efficiently with an array or a linked list. With an array, say some brand new player comes in and they take the top score right away, right out of the gate. Well, now if your top score is at index 0 is the way I would build this, now you have to insert at index 0 and move everybody else down by one position. Physically in memory, you have to copy all those values down. Plus your array might need to be resized. It's going to have to be resized every once in a while. It's going to be O of n to insert. In linked list, you can insert in constant time. It's just manipulating some references. That's easy. If we prepend from a link to a linked list, it's O of 1, very efficient, constant time. Doesn't matter if there's a billion elements in that linked list. Prepending, you already have a reference to the head. Create a new node, it refers to the head. It is the new head. Done. But finding where to insert can take a long time. So if you have to insert in the middle of the list, you have to do dot get next, dot get next, dot get next, dot get next, and go through half of this list and over 2 to find where to insert and then insert right there. We have no efficient way to do that. You can do like we did with a queue and have references to the beginning and end, and you can have a doubly linked list so you can go in both directions. But when you got to insert in the middle, well, you got trouble. Okay, well, I'm going to store a reference to the center node as well. Okay, now I have to insert at the 1/4 and 3/4 spots. And all those are still constants. That's still going to be O of n. No way to get around that in a linked list. BST, on the other hand, we can insert in log n time. We can also remove in log n time. We're not going to do that in 116. But if we can remove and insert in log n time, then when a score updates, we can think of an update as a removal and an insertion. If they're both log n, that's overall log n time. So we can efficiently maintain sorted order with dynamic data. If your data is static, it's never going to change, and you just have to sort it one time. Whatever, use an array or a linked list. Do whatever log n algorithm you like. But if the data is going to change and you need to keep it in sorted order, you can do that in log n time for each change to the data with a BST. So that's one of our big advantages to a BST. And what does log n really mean? Well, with this tree, we have 7 nodes, and we can kind of round that up to 8. It's going to be 2 to the h minus 1, so it's always going to be off by 1 for a fully balanced tree. But we can think of this as 8 nodes. And our logs, we always take as log base 2 in computer science, specifically here because it's a binary tree. We have 2 child nodes to each node. So log base 2 of 8 is going to be 3. And that's exactly what we have here. We had to check 3 nodes for a tree of size 7. So we checked log n nodes, which is less than half the nodes. So that's pretty good. Less than half the nodes that we had to check because we have a log n runtime algorithm. Barely less than half, but less than half. But how does this scale? Like how does this go to, how does this scale to larger trees? So say we have a fully balanced BST with 1,000,000 nodes in it. What's going to be the height of this tree? So more succinctly, what's log base 2 of 1,000,000? Now you know from math class that log grows really slowly, but how slowly does it grow? 1,000,000 nodes in our BST. How tall is that tree going to be? What's log n? What's the runtime of our find and insert with 1,000,000 nodes? 20. It's just 20 nodes we'd have to check. If you have a binary search tree with 1,000,000 nodes in it, and I ask you if that BST contains any specific value, assuming the BST is balanced, you could do that by hand. You could just check 20 nodes and get to a null or find the value. You might find the value even sooner than that. 20 nodes you have to check. That's it. This is how them 20 question games, when it'll ask you 20 yes or no questions, and at the end it'll be like, you were thinking of this, and you can think of like just about anything. That game can have 1,000,000 things that you could possibly be thinking of all coded into it, and then have one big decision tree where yes, no, yes to the right, no to the left, and go down the tree and come up with 1,000,000 different possibilities with just 20 yes or no questions. And to be fair, the 20 question games are a little more complex than that because it has to account for sometimes the user will give incorrect answers. So it has to do a little bit more than just a binary tree. But it could, if somebody always gave the right answer, this is how the math checks out. 20 questions, 1,000,000 possibilities. And if you went up to 1,000,000,000, 30. Log base 2 of 1,000,000,000 is actually a little less than 30. This is a little less than 20. Log base 2 of where am I at? Billion, trillion, 40. Quadrillion, 50. Every time you had 3 zeros in base 10, the log base 2 of that number goes up by 10. Just 10. A factor of 1,000 more multiplied is only going to add 10 to your runtime. Logs are powerful. Logarithm, we love when we see our algorithm is some log runtime. we get is ecstatic. That is ridiculously efficient. How slow logs grow is much, much to our advantage in computer science, if the tree is balanced. But I was very careful to create balanced trees. In the slides and in the example I came up with, I had to think a little bit when I was inserting values into the BST to avoid this situation. If I insert values in sorted order, now I'm going to have trouble. I insert -3, that gets to be the root. I insert 2, we say, is 2 less than -3? False, go right. Is 4 less than -3? False. Is 4 less than 2? False, go right. All the way to 14, go right, go right, go right, go right, go right. Our algorithm is going to effectively create a linked list if we insert in sorted order or reverse sorted order. We have to be very careful of the way we insert, the way we coded our BST today. So this kind of just blows all the efficiency out of the water. The reason to use trees is efficiency. That's what I'm pitching to you. And we have this glaring issue where we can have horrible inefficiency and just end up with a linked list. And everything's O of n at that point. Everything sucks at that point. Just use a linked list if you're not going to be careful with your BSTs. So there are solutions to this that I'm going to present as questions. How we want to know, how do we insert and also remove nodes in log n time while maintaining the property of a BST, the less to the left, greater to the right, and maintain tree balance. All in log n time. I know that's the first thing I said, but it's really important. Doing all that in log n time. How do we do that? And I'll give a very short answer. The short answer, you're going to learn about red-black trees and AVL trees in CSE150. In short, it's going to fix the imbalances as they're detected. And I believe it would do it right when 4 is inserted. It would do what's called a rotation and rotate these nodes such that 2 will be the new root node, -3 will be its left child, and 4 will be its right child. And as we add more nodes, it'll eventually rotate again and fix itself. So it'll auto-correct as it starts to detect imbalances so it can remain balanced. And doing all that in log n time is pretty neat. It manipulates the references so it doesn't have to copy large chunks of the tree. It'll manipulate references to do that in log n time. All that is CSE250. I'll let them show you exactly how to accomplish that. You're going to learn all about it. How to actually get true efficiency, even if you insert in sorted order, still getting log n all the time with no worries. And then, of course, the duplicate conversation will always be there. Okay. 17 minutes. So in the other lecture, this is where I switched to live coding, but we've been live coding the whole time, so it's less crucial that we have this, which is okay that we have less time. We had half an hour when we got to this point in the other lecture, so we're not even completely far off. But I got to decide how much I want to do. Let me skip the testing. As much as it pains me to say that, I think I'll skip the testing part of it. Yeah. Oh, I'm still not going to think of a rock. Think of a class name. So what I want to do is create a binary tree of... Well, I have to create it. I do have to do a test case, don't I? A binary tree of an object type. All the lecture examples were ints. And in the slides, I have one example that's strings, but in your homework, I'm asking you to create a binary search tree of songs. So I want to get at least one example in there of a BST of, not a BST, a binary tree. I'm not going to do it as a BST of, or maybe I should. Maybe I will. No, I'm not. I'll post the solutions to the practice traces. I don't have time to do them in lecture, though. I wish I did. It'd be nice to give a whole tutorial walkthrough of them. I just don't have no lecture time for that. So let's create a binary tree of some object type, which I'm just going to create some rocks here. Private weight. Oh, I forgot the type. Private double weight and private double name. I just want two values, and one of them is, with one of them being numeric. That's my goal here. I just needed anything. I'm going to generate my constructor and my getters and setters. And I want to create tests for these. Mostly just to show some usage. It could just be a main method for what I'm going to do with it. And I don't know, rock algorithm. Sure. And what I want to write is a method total weight that's going to sum up all of the weights of all of the rocks in a binary tree of type rock. And we call it rock tree. And I'm just going to stub this out for now so I can get my setup for my testing. I'm going to use the test annotation from org.junit. That's the right one. Public void, blanking on it, test rock tree sum. Sure. And then new binary tree node of rock. Rocks equals, I have to call this rock pile. New binary tree node of new rock 3.1 shale. And we have to come up with rock names. And here's where I'm going to use a different strategy of creating a tree that I promised way long ago in this lecture. Different way of creating the trees. As long as you get the values in the trees, whether you're using the getters, the setters, constructors. This I'm going to use constructors inside constructors to give you something new. But I'm going to create a new binary tree node where the first argument is the rock that I'm putting at this node. Second argument is left. Third argument is right, just like we've seen the whole time. But instead, I'm going to hard code in the right node. I'm going to create the node, call this constructor inside a constructor call. Which can get a little tricky. I would never do this on a quiz because tracing this is kind of a pain. Just seeing where all the code is coming from is a bit painful. But for this example, I just want to show you something new. Let's see, 6.5 granite. And then its left is going to be new binary tree node, new rock. I have to think of another rock name. Shell, granite, volcanic. Is that rock name? Oh no, this is where we volcanic sediment. I'll go with that. 'Cause I gotta go on. And then null. No, I want to cap my tree right there. And then without fail, I will always imbalance my parentheses because this is hard to read and confusing, which is why you shouldn't really... Oh yeah, I should be thinking of Minecraft. Obsidian. I got all kinds of rock examples there. So I'll trace through this. New binary tree node, its value is this rock. Left is null. Right is this thing, which ends right here. So one of these parentheses is the end here, so I had an extra one there. So then this one has its rock, its left, and it doesn't have a right. That's what I'm missing right here. And then this needs to get capped off with a semicolon, and then I can let my formatter take care of everything else. So there's my rock pile, and I want to get my double actual equals rock algorithm. Did I make that static? I did not. I'm going to leave it non-static. New rock algorithm. Rock algorithm. No, really I would make that static because it doesn't, if a method doesn't rely on any instance variables of the class, you should make it static. So that's why we still do see some static methods from time to time. So this one should be static, but I'm going to make it non-static just so I have more stuff to show you. Algo.total weight of my rock pile. My double expected is, I didn't do the math yet, 17811.1, which is hopefully correct. And then assert equals, ID is not going to help me out on that. Sometimes with external libraries, you're not always going to get the most help. Actual, and then if you're comparing two doubles, make sure you allow some tolerance. Oops, I forgot I switched my keyboard. I switched Control and Alt. So when I see Alt, I hit Alt, but I switched them. And then make sure you have your tolerance, 0.001. Never just assert equals. If you don't have that, IntelliJ will yell at you. That didn't even get the right, that didn't get the right import anyway. It'll yell at you. It'll say, "What are you doing? You can't compare doubles like that. That's you're insane if you're trying to do that. Definitely don't do equal equal. That's insanity as well. That's asking for incorrect on a your test failed a correct solution. You need some tolerance." And a brand new one. I just saw a brand new one this semester. Even after doing this for so long, I still get surprised from time to time. I saw this in someone's code. They knew to put some tolerance there, but they said, I don't want any tolerance allowed. I don't understand what truncation errors are. I didn't pay attention to that lecture. I just know I'm supposed to have a third argument here because that's what the IDE told me. And they put a 0 there. I'm like, what? I just said, you need to study truncation errors. So here's my test case. Just one test case. Obviously, it's not a full test suite. It's not going to test much. But it's going to make sure I'm going through my tree at least a little bit. It's going to make sure I'm not completely out to lunch on it. And then our algorithm. I want to set up my sum. This algorithm isn't actually going to be all that hard. Set up my sum of 0.0, return my sum, which I'm going to call it total. I'm going to set up my accumulator variable. And for this algorithm, I would say if the tree is empty, return 0.0. Like that would be one of my bullet points if this were a homework assignment. And I usually like to set up things in a way where the edge case can just wash out. If there's only one edge case like this, where it can just kind of wash out of my code. So I'm going to say if rock tree is not null, because if it's null, that means it's empty, and I should return 0.0. If it's not null, I'm going to do all my stuff. But if it is null, I set up my accumulator, I don't do anything, and then I just return 0.0. So if rock tree is null, my base case doesn't need my edge case doesn't need a special chunk of code. I guess you could say the conditional is a special chunk of code, but like I'm not putting any else on this or anything like that. I'm just letting it wash out and using the same variable that I use for my actual logic. So anytime I can have my code have dual purposes like that, I usually like to. As long as it doesn't compromise readability, I like doing that. And then rock tree. Oops. And then what I want to do is make my recursive calls. My total is going to sum up total weight of rocktree.getLeft. Now this might be null, but in my recursive call, I'm going to have my null check right here before I use the dot operator on rocktree. So I'm going to be okay with that. I'm not going to get a null pointer exception. And then total weight of rocktree.getRight. And then the line that's actually going to do work, total plus equals rocktree.getValue.getWeight. So remember, the value is going to be an object of whatever the type is, which is rock. So this resolves to a reference to a specific rock, and I want to get that rock's weight with the specific getter. That's what you have to do with songs as well. To get the value and then get the specific... actually, do you have to do that? For the utility method. You get the value, that's going to be a song, and then assert that that song has all the properties that you want. Is it equal to the song at this node in the other tree? Make sure they're all equal by calling your other utility methods. And we're going to return total. And that's it. Not too complicated of a method. Again, recursion really helps us out here. If we were not using recursion here, this method is an absolute nightmare to write. And you'll get null pointer exceptions and errors and logical errors and all kinds of issues while you're debugging a really complex method. Because you're doing a lot of extra work, something way beyond 116. I would never ask you to do something like this without recursion in 116. Please, please use recursion. It'll make these tree algorithms way easier. I would not even attempt to write that without recursion. I would never want to do that to myself. I certainly wouldn't want to do it to all of you. And we get the value that we expect. So let's get back into the debugger here and see what happened. Make sure that we got, make sure we understand exactly what happened there. So my rock pile has the value 3.1, and left null right is a new node with 6.5. Its left has the value 1.5, and its right was null, and everything else was null. We get into total weight. Total is 0. Rock tree is currently the root of our tree, so it's definitely not null. So we're going to get left and make a recursive call on the left, which is null. So left of the root was null. So total is 0. Rock tree is null, so that's false, and return 0. So we add 0 to the total. Make another recursive call on the right. This time right is an actual node, 1115. So we're going to make a recursive call to total weight where rock tree is 1115, which is not null. So we're going to make a recursive call to the left, which is 1118, another actual node that's not null. So at this point we have 3 calls to total weight on the stack. One where rock tree was the root, which had all of the things. One with an intermediate value, which had some of the things. That's not the best way to say that. And then the current call, which is one of our leaf nodes where left and right are both null. But this call, this stack frame, is kind of pretending that this node is the entire tree. That's what recursion is supposed to do. It's supposed to treat whatever it's given as though that is the entire input and its job is to create a sub-solution. It's creating a solution as if this tree were the entire tree. And that's what it's going to do here. It's going to do get left, which is going to return 0 because it's null. Get right, return 0 because it's null. And then add its weight to the running total. When it adds its weight, now total is 1.5. So if this node were the root of a tree, the total weight of that tree is 1.5, and this call is returning 1.5. So when we get back to this stack frame up here, which is waiting for its left recursive call, its left subtree is just that one node. Its left recursive call got the total weight of just that subtree, of that entire left subtree, which is just one node. So it adds that to its total, gets its 1.5. Its right is null, so that's not going to change anything. So then it's time for it to add its own value to the running total, add 6.5 to the 1.5, and return 8.0. It's going to return 8.0 to our original recursive call, which was making its right recursive call. So it got the weight of the entire right subtree. I should have gave it a left subtree too to drive that point home. But it got the sum of its entire right subtree. So we made a recursive call, and we just assumed that this is going to return the total weight of the right subtree of everything over to the right. And it did. It did its job, and it returned 8.0, the sum of these two values to the right. The left did its job. It returned 0.0. There's nothing over there, so we returned 0.0. Now total, it's going to add the weight of the right subtree, which is 8, add in the weight of this node, which is 3.1, and return our 11.1. Returns the correct value here. We assert, we account for truncation errors, and our test passes. Can you only run the debugger if you have a main method? Man. Oh, red dash. I don't even understand the question. This isn't a main method. This ain't no main method. I just ran the debugger. Hell no, you don't need a main method. Technically, you need a main method at some point. Like, way down the stack frame, there is a main method way deep into the JUnit stuff. But you can use the debugger on your test cases. You certainly can run the debugger in your testing. Either testing or your main method. Write a main method or a test case. Either way, set a breakpoint, and then click the debug button, and you get that debugger. And then the two main buttons that I've been pressing throughout that, step into, which is going to go into any stack frames, and step over, which I'm using to skip over some things. Like, for example, I don't want to go into this call of total weight. I certainly don't want to go into this get left call. So I'm going to do step over. That just skips over that whole line. It still executes the line, but it doesn't bother me with the details. Get value and get weight. I don't want to go into two getters. Like, that's just a lot of extra clicking. It didn't even go into the second one because I didn't click on it. But step over can save you time. Or just always click step into. If you only ever click this button, that's perfectly fine too. You're going to get all the information you want. But as you get more comfortable with the debugger, you can start using the step over to skip over all the getters and setters and all that stuff that you're not always interested in. Okay, and we're 3 minutes over, so I better shut this down. I'll take a quick break, and then 2 o'clock I'll start taking y'all in office hours. Good luck on the midterm. I'll get the solutions posted for the practice ones posted to Piazza before I go to bed today. Promise that much. I think that's all I need to say. All right, take care, everybody. If I don't see you in office hours, good luck on the midterm.